Okay, the SIR model. The SIR model is a simple model of an epidemic of an infectious disease. The S stands for susceptible individuals, those capable of becoming infected. The I stands for infected individuals, those capable of causing infection. And the R stands for removed individuals. Those individuals no longer able to contract the disease because they have recovered with immunity, have been placed in isolation, or they have died. This model is composed of three differential equations, which can be represented as the rate of change of susceptibles with respect to time, which is beta times S times I, negative beta times S times I, the rate of change of infectives with respect to time, which is beta times S times I, minus gamma times I, and the rate of change of removed individuals with respect to time, which can be represented as gamma times I. However, this model has become too complicated and tedious to work out, but a cousin, per se, of the SIR model is the logistics growth model, which takes out the removed individuals and simply simplifies the S and I individuals into one differential equation for a population, which can be represented as the rate of change of the population with respect to time, which equals K times P times 1 minus P over M, where P is the population at time T, K is a constant in proportionality, and M is the carrying capacity, which is the max number of population. Okay, the logistics growth model can be seen as a separable differential equation, and therefore you can solve for P of T by separating both sides, integrating, and then solving. So when you do that, you get the carrying capacity divided by 1 plus A times e to the negative kt power, where A is represented as the carrying capacity minus the initial population and divided by that initial population. Okay, let's do an example. Let's say the carrying capacity is equal to 10,000, the initial population is equal to 500, and let's say that within the first year the population triples, so P of 1 equals 3P. We can plug all of these numbers into P of T to get 10,000 over 1 plus A, which is this right here, times e to the negative kt power. And then we can simplify this to get 10,000 over 1 plus 19e to the negative kt. Because the population tripled within its first year, you can do 3 times 500 to get 1,500, which equals P of 1, and set the equation P of T equal to 1,500. And when you do this, you can then solve for K. And when you solve for K, you get negative K equals the natural log of 17 over 57, which can be plugged right into the equation since this is negative K. And when you do that and simplify, you go from this to this, which is 10,000 over 1 plus 19 times 17 over 57 to the power of t. And this equation can now be used to solve for the population at any time t.